So I'm gonna go over worksheet 21 here. And most likely people won't be here asking questions, so I might not go into as much detail as I do on most other recordings. So if you watch this and you have a question that you want answered, feel free to reach out to me by email or over Canvas and ask, and I'll make sure to give you as much detail on my answers as possible, like I would if you were here right now. So first, there's a true-false section. And the first question is, acetoacetic ester synthesis is a reversible reaction due to the formation of carbon dioxide gas. So I'll start by showing you an example of what a typical acetoacetic ester synthesis would look like. You'd start with a structure like this, where you have a ketone and an ester beta to each other, and they share this alpha position between them. And then it's usually a 3-step process. The first step, you add a base. In the second step, you add an alkyl group with a leaving group. And in the last step, you add acid, heat. So again, like X is leaving, like chlorine, bromine, OTOS. Those are the main ones, like halogen and OTOS. So you had a base, something with a leaving group, acid and heat. I went over the details of this reaction kind of in depth on the last worksheet, so you can refer to that recording for the details. But in the end, the product you get is acetone, where we've added an alkyl group to the alpha position. And then you get an alcohol, and that comes from the ester. Again, like you can refer to the last worksheet for exactly where that comes from, like how it forms, but it's from the ester. And you form carbon dioxide. And, you know, carbon dioxide is a gas. And in the past, we've shown arrows like this pointing up when a byproduct that forms is a gas. So we can do the same thing here. And it's important to show that because, like, if you did this reaction in like an open round bottom flask or something, and then the carbon dioxide formed, like you'd see fumes leaving the flask, and then they're gone. They're not going to come back. And if the product is gone, then there's no way to go backwards to what you started with. So it's an irreversible reaction. You can't go backwards. This is saying it's reversible, so it's false. If a gas forms, it's always going to be irreversible. The next one is aldehydes, and aldehydes can be treated with base to undergo direct alpha alkylation reactions. This one is false. There's a couple carbonyl compounds and stuff related to carbonyls that you can do this kind of reaction with, direct alpha alkylation reactions. These are where you add a base and then you add an RX and it puts an alkyl group on the alpha spot. But you can't do this with aldehydes because they're too reactive. They end up doing aldol reactions if you add a base to them. So you cannot add a base and then have it react with something else to do an alkylation. It's always going to do aldol before it does anything else. The next question is, aldol reactions always involve one electrophile and one nucleophile. This is true. I'm gonna go over the mechanism in a bit. But if we had like acetone, or I'll do both. If we had acetaldehyde, like one component of the reaction would be an enolate where we've deprotonated the alpha proton. And then the other component of the reaction would be another aldehyde. And the enolate will attack the carbonyl carbon. And like we have one nucleophile because we have the enolate, we have one electrophile being attacked. So, yeah. That's true because we have nucleophile and electrophile. Okay. Next is aldol reactions can occur under acidic or basic conditions. This is false because we are using an enolate as our nucleophile, and that's always going to be the case. Color. You need an enolate, and to form an enolate, you need a base. So you can't use an acid to form an enolate. Okay, next one. Direct alkylation reactions are base promoted. It's true because indirect alkylations, as an example, one equivalence of a base. And then the second step, you add something with a leaving group. And like that would be the typical product. But what's important for this question is you're adding one equivalent. You're adding, like, if there was 1 mole of the ketone, you're putting 1 mole of the base. And you're putting a full equivalent because it's not going to be a catalyst. It won't be regenerated. It's going to be consumed. The base is going to be consumed. And that's what makes it base promoted. If you use one equivalent, it's consumed. If you're using a catalytic amount, the base is regenerated. So just be aware of these distinctions because we're going to see examples of both kind of coming up in the class. And the last one on question 1, aldol reactions are typically done with strong bases such as sodium hydride. This is false. We usually use bases like sodium hydroxide or an alkoxide, but they wouldn't want to use a strong base like hydride. Okay, so that is question 1. Here we have a series of malonic and acetoacetic ester questions. And the first thing you should do if you see a structure like this is figure out which one it is, because once you do, you should know the details of the reaction. And again, I went over it on the last worksheet, but without worrying about the details, you can kind of figure out what the product will be without thinking about it too much. And I'll explain how that is the case in a minute. It's like this structure, we have two esters beta to each other because we have these parts attached to the carbonyl. So it's two esters beta to each other, which means we're doing malonic ester synthesis or ME synthesis. And the product of malonic ester synthesis, if you go through all the details of it, you'll see this is always the case. Acetic acid is a part of it, and this is acetic acid, just a carboxylic acid with two carbons. And then the other part of the product in malonic ester synthesis is we add whatever alkyl group that we added to the alpha position. So here we added propyl chloride, 3 carbons. So I'm just going to put a propyl group here at the alpha position, alpha to the carboxylic acid. And then that's the product. And again, like this is always going to be the case if you're doing malonic ester synthesis, where you have these two esters beta to each other, and you have conditions that look like this, then it's always going to be a substituted acetic acid product. Just put the alkyl group that you added in the second step, alpha to the carbonyl, and then you're done. And the next one is a little different because we have one ester here, and then we have a ketone over here instead of a second ester. So this is going to be acetoacetic ester synthesis, or AA. And this is what we're doing if we have a methyl ketone ester to each other. Just like the last one, malonic ester had a characteristic product, acetoacetic ester has a characteristic product. It has an acetone as a part of the structure. And then again, just whatever alkyl group you're adding. Here it's an ethyl group, so I'm going to put an ethyl group here. That's the product you end up with. You get a substituted acetone as your product. Okay. Next one has two esters beta to each other. So this is malonic ester synthesis again, or ME. So right off the bat, if this is what you're doing, you can just start by drawing acetic acid without thinking about like what exactly the product will look like. You know, this will be a part of the structure. And then we add this alkyl group to the alpha position. And we're going over a lot of reactions now that make new carbon-carbon bonds. And sometimes we're adding large structures as these things that we're adding alkyl groups. This isn't too large, but like with aldol reactions, we'll see larger structures. And I think it's important to either count your carbons in like the substrate and the product very carefully, or number them. Like I'll number them here. The carbon with the chlorine in step 2 was carbon 1. And then these numbers are kind of arbitrary. You could do different numberings or give them letters as long as you have something that makes sense to you. And then like the attack that happens is an enolate attacking the carbon with the leaving group. So it attaches the carbon 1, which means this is carbon 1, this is 2, and 3 if you cross-reference it. And then the methyl group is carbon 4, 2. So if you number them like this and then you number it in your product, you can make sure you attached it correctly and that you put the right number of carbons just to make sure. And this might seem like a waste of time, but just yesterday when I was going over this, I accidentally drew this, and then that has not enough carbons, that's only 3 carbons, and the extra methyl group is in the wrong spot, just like there's a lot wrong with it. But if you were on a test, you might not notice because it looks a bit similar to what we were adding. So again, just number the carbons or be very, very, very careful because it's easy to make mistakes. I made one and I had the answer key right in front of me. Okay, next one has a methyl ketone and an ester beta to each other. And we're doing a similar sequence of reactions. We have 2 extra steps than usual, but it involves adding base and an alkyl halide and base, and alkyl halide, and then acid and heat again. So it's a similar process. This is acetoacetic ester synthesis, just like before. So again, a core part of the structure that you know is going to be around is acetone. And then we're adding 2 alkyl groups. In step 2, we add a methyl group. So I'll just put that here. That came from step 2. And then you add a butyl group in step 4. You add 4 carbons. So 1, 2, 3, 4, something like this. And that's it. Because again, if you're doing acetoacetic ester synthesis, you're always going to have a substituted acetone as part of the structure of the product. And I didn't say this yet, but the conditions of these reactions are important. Like Okuda is probably going to specify the 1 equivalent of base. If he doesn't specify it, then that would mean you're putting excess. And then if you were putting excess, that would mean like, because there's 2 protons here, you'd be adding enough to deprotonate both of them and form like multiple enolates. And then all those enolates could react with the alkyl halides multiple times. So just as a sort of side example, I'll say like specify 2 equivalents of oxide and then 2 equivalents of, just put something specific, methyl chloride, and then it's that to be the same, acid and heat. This is acetoacetic ester, so start with acetone. But then like we added 2 equivalents of base and we put 2 equivalents of the alkyl chloride. So we're going to add 2 of these instead of just 1. And if you didn't specify equivalents, it would be excess, which would be the same idea. It would react this way. So pay attention to the number here, 1 equivalence, 2 equivalents. If he doesn't say it's excess, because it makes a big difference in how these reactions work, like what products you end up getting. And the last one on this page, this is different from the other ones because it doesn't have that small structure with just the carbonyls and nothing else attached. Like if you look at this that I have circled and you compare it to the previous one, like it looks somewhat similar because we have a ketone and an ester beta to each other, except this one on the bottom, like this isn't a methyl group, it's a whole larger structure. It's a cyclohexyl group. But it's the same core, like ketone and ester, beta to each other. And it's going to react similarly to acetoacetic ester. It's not going to be the exact same product. It's not going to be like a substituted acetone because it's not acetoacetic ester synthesis, but it's going to be a similar process. So like, I'll go through the details just so it makes a little more sense since it's different this time. But like, you add the base to form the enolate on the alpha position. And then in the second step, you add the ethyl OTOS. OTOS, remember, is just a good leaving group, like a halogen is. So the enolate attacks the OTOS. And this is after step 1 and step 2. We put an ethyl group on the alpha position. And I won't go into too much detail on it. Again, you can refer to the last worksheet. But remember that when we add H3O plus and heat, the H3O plus part is gonna do hydrolysis on the ester. It's gonna turn it into a carboxylic acid. So it's gonna convert the ester to a carboxylic acid. And then if you draw that structure, when the ester is a carboxylic acid, you have a ketone and a carboxylic acid beta to each other. If you heat that, you lose the carboxylic acid as carbon dioxide. So we're going to lose the ester. That's basically what happens from the third step. And that's what was happening before. I just was not talking about it because I talked about it before. And it would take too long to discuss the details every time. But in sort of summary, H3O plus in heat basically gets rid of the ester as carbon dioxide. So that part in the structure that I circled is just going to be gone in the final product. And we still have the ketone. And then we also, remember, put this ethyl group here on the alpha position. So that would be the product. So just be aware that like this reaction, like that we're doing with malonic ester and acetoacetic ester, you can do it in structures that are larger than these. And in those cases, remember, it's not going to be like an acetone or an acetic acid product. Like if it's not these smaller structures I have circled up here, it's not always going to be that simple, but it will be the same idea. And if you know the details, you can work through it and figure out what the product will be. Because in the end, you're just adding an alkyl group and then you basically just got rid of the ester as carbon dioxide. So yeah, just practice the details a few times, be familiar with it, and then whatever context he throws it at you, you'll be prepared. Okay. On the last worksheet, I gave you a bit of misinformation, and I'm sorry, I didn't mean to do that. I was teaching it based on how it was when I took the class with Okuda a few years ago, and he's approaching it from a different angle. He's not having you worry about as much details, and he's not really approaching it from the way I expected. So that's why I told you wrong information. So all of these on question 3 are direct alkylation reactions, where we're adding an alkyl group to an alpha position. And I told you guys in the last workshop, on the last worksheet, that the alkyl group would add to the less or the more substituted side. The more substituted side. Like if you have a ketone and you're doing a reaction like this, I was saying it would add to the more substituted side. So like this structure, it would add here because that's the more substituted side, alpha to the ketone. And I said that because like if I draw an intermediate that would lead to that, like where you have an alkoxide and you have an alkene, if you compare these two alkenes, this one that I drew, that I have circled, would be a more stable alkene because it's more substituted. And a lot of the time, that more stable intermediate is going to be the one that gives you the major product. And that is how Okuda taught it to us in the class when I took it. So that's why I taught it that way. But I'm assuming based on the examples he showed in lecture and just how he talked about it, you're only going to be looking at these reactions with LDA. I showed examples of like sodium hydride and NaNH2. And as far as I can tell, you're not going to have to worry about these bases being used for this reaction. Just worry about LDA. And that's a bit important because this is LDA. It has a nitrogen with a negative charge, and then there's a lithium counter ion. And we have these two isopropyl groups attached to it. The drawing doesn't really do it justice, but those isopropyl groups are really large. They take up a lot of space. So this is like a really bulky, sterically hindered base. And because it's bulky and sterically hindered, it generally prefers taking less hindered hydrogens because it's easier to reach those. But that means that you're forming the less stable alkene. So it might not be the first thing that you would consider, but this is why this is the correct way to approach these reactions. Because you are using a very bulky base, and again, as far as I can tell, you're only going to have to worry about this base. So since it's bulky, it prefers taking the less hindered protons. It's like in this structure, it's going to prefer taking this one on the right because that's less hindered than the left side. Which means even though this is what I said, like that's how the reaction would go, it's actually going to follow reacting with this intermediate because that's where the LDA will go. So you would have this enolate, and then the rest of the details are the same as I was saying. It is an SN2 process, so look out for tertiary substrates, but this one is secondary, so it works fine. And in the end, we put that isopropyl group on the alpha position. And just some other things, the conditions are very important for these direct alkylation reactions. So make sure to look for all of these details. one equivalent, it has to be one equivalent. It's never going to be like catalytic or anything else. He's always going to specify one equivalent. So this is a clue of what reaction you're doing. And then this temperature, negative 78 degrees Celsius, is another clue. He discussed in class like why it has to be cold. Basically, like if you don't cool it down, you're going to do other reactions. So we have to cool it. Otherwise, it's too reactive when you form an enolate. But you can just remember, if you like, that like it has to be cold. So these two parts that I've circled, and like you need a base, that's one equivalent of the base. These are hints that this is the reaction you're doing. So just make the connection between those. Because I don't believe you're going to see other reactions where the temperature being cold is emphasized in the class. So you can make the connection there. That might help you. Okay. The next one, we have another ketone, and we're adding one equivalent of LDA at negative 78 degrees Celsius, and then another alkyl halide. We have two possible spots the enolate could form, here or here on the right side. Again, it's going to want to form on the less hindered side because it prefers, LDA prefers taking the less sterically hindered protons. So we're going to form an enolate here. Our substrate is this ethyl chloride, which is primary. So this works fine for an SN2 reaction. And we get our product where we add an ethyl group to the alpha position. And last one, again, similar conditions, one equivalent LDA, negative 78 degrees Celsius. And then we have this OTOS substrate that we can use to add an alkyl group, hopefully. But this time, instead of a ketone, we have a nitrile as our functional group. However, this doesn't make it so nothing is going to happen. This will still react similar to a ketone, because what's special about ketones, like what allows them to do these reactions, and other carbonyls in general, it's like if you draw this enolate, remember we can draw a resonance form with the carbonyl, and resonance stabilizes it, so that makes it possible to form this in the first place. And similarly, if we have a nitrile and we have an enolate alpha to the nitrile, that's a negative charge next to a triple bond. So again, you can draw a resonance form, which stabilizes the enolate and makes it possible to form in the first place. So nitriles can react similarly to carbonyls in these reactions. So even though these are different from carbonyls, like it looks like a very different functional group, they behave the exact same way. If you add a base, you'll form an enolate, and then the enolate will react with the thing with the leaving group. Okay. Actually, I am just going to erase this top one so it doesn't look as crowded. So in the end, we add this to alpha to the nitro, and that's the product. And I'm gonna put some stuff in the bottom left here. Just as a general note, you can do direct alkylation reactions, ketones, esters, and nitriles. Those were the functional groups that were discussed in specific in lecture, and I think in the book too. So I believe these are the only ones you have to worry about: esters, ketones, and nitriles for this kind of reaction. We said earlier aldehydes can't do it because they do aldol reactions. And other functional groups don't work with it for one reason or another, but these are the main three to consider that can do these reactions with these conditions. So if you want to memorize that, it might be helpful. Okay. Typically, I don't believe you're going to get this hint where he puts a 2 in front of the starting material. I did it here just because this is a new reaction to you guys at the moment. So it was to kind of hint at what's happening. But if you ever see an aldehyde or a ketone, and on the reaction arrow, all you see is catalytic sodium hydroxide, you should start to make the connection that this is conditions for an aldol reaction. So catalytic sodium hydroxide is always going to be aldol conditions if it's with an aldehyde or a ketone. And I put the 2 here because, as I discussed a little bit earlier, these reactions involve 2 aldehydes or ketones reacting with each other. So that was a sort of hint to say this is the kind of reaction you're doing if you're not sure. But again, I don't know if you're going to get that on a test. So remember the conditions. And you should know the mechanism for this. It's a bit long, so he might do something similar to what he did with the acetal mechanism on the last exam, where like you start with an intermediate and he asks you to finish it, just because going from start to finish takes a long time. I don't know if he would do that. I'm just saying he could to make it a little easier on you guys. But I would recommend knowing the whole thing. We're adding a base here, so even if you weren't sure like how this is supposed to stop or how it's supposed to start, like you don't remember, you can think about like, well, what does a base want to do? And remember, bases take protons, typically take acidic protons. So the hydroxide is going to want to take an acidic proton, and the only hydrogens that are acidic in this structure are the ones alpha to the carbonyl. Remember, we've talked about how alpha hydrogens are a bit acidic. They have a pK of like 20, which isn't super low, but it is low enough to react a little with this base. And that would be the first step of this mechanism. The hydroxide will take this alpha hydrogen. And that will lead to the formation of an enolate. Okay. And then I kind of showed you guys this next step earlier on true false. We have an enolate, but we haven't converted all of the aldehydes to enolate because we're only adding a small amount of hydroxide. There's not enough to turn all of these aldehydes into enolates, which means that there's still a little bit of the starting material floating around, the neutral aldehyde. The enolates can behave as a nucleophile because we have that negative charge on a carbon. And remember in chapter 19, I believe it was, we looked at aldehyde and ketone reactions. And remember, in those reactions, the aldehyde or the ketone was always an electrophile. Specifically, the carbonyl carbon is an electrophile. So these two can react with each other the same way we did before. The nucleophile attacks the carbonyl carbon, and you push the double bond up towards the oxygen. And that leads to the formation of an alkoxide. And we don't want it to stay negative. We don't want it to be an alkoxide. So it's going to get protonated. And it will be protonated by water specifically. In the first step, we used hydroxide to take this proton here. So now we're going to take that proton back from water that formed. And that will lead to an alcohol forming. And then we also formed hydroxide again. So the base catalyst was regenerated. And this is a neutral product. This is the Aldol product that I have drawn here. And it's called an aldol. That might make sense because like the ald part is referring to the aldehyde here. And then the ol part is like the alcohol ending, like with propanol or methanol, like it ends with OL, and we have an alcohol here. So the name of it just describes the functional groups. And this is a product you get, but a lot of the time, you can also get a second product from these reactions. It'll keep going. And unless he specifies otherwise, if he asked you to show a mechanism, I would suggest going all the way. Again, unless he specifies otherwise. So we just regenerated our base catalyst. So now we have more base floating around. And bases still like to take acidic protons, as I said before. There's still one more hydrogen here, alpha to the aldehyde, that still has a relatively low pKa. So the base is going to take this proton and form another enolate. And then this enolate is going to do a sort of elimination reaction and kick out the alcohol. So it's going to form a double bond and kick out the alcohol. And that would be the end of the mechanism. So I'm just going to oh, well, never mind, that alcohol is not there anymore. You end up with a double bond like this. And the double bond is on the alpha and the beta positions, and it's conjugated with the aldehyde. So yeah, this is the final product. You can also get a conjugated product, like with the alpha and beta positions having a double bond. So it is a bit of a long mechanism, but a lot of it is kind of new stuff or old stuff, just in a new skin. Like these first couple steps after the enolate forms and the enolate attacks the other aldehyde. Remember from chapter 19, like in these reactions, a typical mechanism would be like the nucleophile attacks the carbonyl carbon. That leads to an alkoxide forming. And then you've added your nucleophile. And then the alkoxide would get protonated. And you would end up with an alcohol. Remember, this was like a typical nucleophilic acyl addition from chapter 19. And these first couple steps were that exact mechanism. Like in the past, the nucleophile was something pretty small. It was like a nitrile or water or like an amine. Like it wasn't a super large structure. Here, this was the nucleophile, the enolate. And this is a relatively small aldehyde, but it's still a kind of big structure. Like it's not just one or two atoms, it's a whole alkyl chain with a carbonyl attached. And they can be much larger, as we'll see in the next questions we go over. So like it's the same kind of process, you're just adding a nucleophile, it's just a big nucleophile. And then in the second step where we have the alkoxide here, it's getting protonated just like it did before, so that you end up with an alcohol and you have your nucleophile attached. And then after that, it diverges a little bit, but like you're starting with this acid-base reaction, and then you're kicking out the hydroxide. And this reforms the base catalyst like it did back then. So, yeah. I would recommend practicing writing this mechanism down, like maybe with some of the questions in number 5, just so you get a feel for drawing it out. Because that's the best way to get used to stuff in the class. Just write stuff out by hand, practice doing it, see how well you understand it. Okay. Actually, kind of missed one of the most important parts. Screen is a bit crowded, so I'm gonna erase this and I'll just draw the 2 products that we got at the end. So these were the 2 products we got. The first one, the aldol product, if you're looking at the carbonyl carbon, this is alpha and this is beta. So the alcohol is beta to the carbonyl. And this is always going to be what an aldol product looks like. They happen with aldehydes and ketones, but every single time the product will have an alcohol beta to the ketone or aldehyde. And then the condensation product will have a double bond between the alpha and the beta carbon that we added. And again, this is always the case. There's no exceptions to this if this is an aldol reaction. So these are some things that I think are important to keep in mind, because if you remember that like the aldol product has this characteristic it has an alcohol beta to the aldehyde or the ketone, and then the condensation product has an alkene. It's similar to the malonic ester and acetoacetic ester problems from before, where like the product always has acetic acid or it always has acetone. So you could always just like, before even doing the question, you have an idea of what it should look like. Like, you know, some part of the structure. And it's the same thing here. Like, if you recognize that this is an aldol reaction, you know the product will have an alcohol beta to a carbonyl. And you can go into it expecting to draw something like that. You don't have to worry about the details as much or try to show the mechanism to figure out what it will look like. You can just go based off of previous knowledge, you know, what it should look like. And I'll kind of show how you could put that into practice with the next reactions. So this next one starts with an aldehyde. And again, we're adding catalytic sodium hydroxide. This time I didn't put the 2 here, and most of the time I don't think this will be a hint you're given. It might be, but I wouldn't count on it. But if you see catalytic hydroxide with an aldehyde or a ketone, remember that is the conditions for aldol reactions. Because it wants a catalytic amount of a weak base, which is what we have. And since we're doing an aldol reaction, I was just saying, like, you know, generally what the product should look like. You should have an alcohol beta to an aldehyde or a ketone. I'll go ahead and draw the nucleophile and the electrophile just to show like the nucleophilic attack that leads to the bonds forming, but this isn't the whole mechanism. So you have your enolate, you have your neutral aldehyde. Enolate attacks carbonyl carbon of the neutral aldehyde, so that is the bond you're forming. When you're drawing the product, you can start by drawing the aldehyde we started with, this compound. And then at the alpha position here, this is where we formed a new carbon-carbon bond. So you can add a carbon here. And this is the alpha position. This is the beta position. So remember, in the product, there should be an alcohol on the beta position. And you can do all of this without like thinking about, well, what did I add? What was this aldehyde? You don't have to think about it too much. You just know there should be an alcohol there because it's an aldol reaction. But then you should draw the rest of the structure. So it should look like this. And like with some of the questions earlier, where I was saying like maybe number the atoms in the structure to make sure you attach it correctly, I think with aldol, this is a very, very good practice to have because this is even easier to miscount or just add the carbons in the wrong way if you're not careful. So I'll say like the carbonyl carbon is number 1, this is 2, 3, 4, and 5. And then this is 1, 2, 3, 4, and 5. So you can see like I have the right number of carbons and they were attached in the right order. So this is correct. But if you don't do that and you don't double check your work, it's very easy to make a mistake. So just please be careful. These are easy to screw up with these large structures. Okay. And unless Dr. Okuda specifies on the test or in class or anything, and he might, I don't know if he'll change his mind, but when I took the class, if we did aldol reactions, we were expected to show both products of the aldol reaction. So this is one of them with the alcohol, but remember there's a second one where you get that conjugated alkene product. So you should also draw that. So again, that means there's a double bond between the alpha and the beta carbons. And then you have the rest of your structure. This is 1, 2, 3, 4, 5. Same order, so similar structure, just with the double bonds between the alpha and beta spots. So draw both unless he says otherwise at any point in class or on a test. Or there are cases where you can't show this second product. And those cases would be if there's not an extra alpha hydrogen here in the aldol product. Like there's still one more hydrogen here. So we went over the mechanism and you saw from the mechanism like we needed another hydrogen to be able to go forward to this final condensation product. But if you didn't have an extra one, you couldn't do that. So that's another thing to like keep an eye out for. If there's not enough hydrogens alpha, then you can only show the aldol product. Okay. This next one has catalytic hydroxide again. This time we have a ketone, but ketones also do aldol reactions. And catalytic hydroxide is conditions for an aldol reactions. So this is another aldol reaction. And just like with the direct alkylation reactions, where they preferred to have the enolate form on the less substituted side because that was less sterically hindered, it's easier to form that. Aldol reactions will also prefer that if you're working with a ketone. So it's going to be the less substituted enolate. It's going to form on the less substituted side every time. So this is applied to both aldol and direct alkylation reactions. Just be aware, like we're going to be forming the less substituted and less sterically hindered enolate every time, which means in this structure, it's going to be the one on the left because that's less hindered than the one on the right. And then this is going to react with a copy of itself, another ketone, where it's not an enolate, and then it's going to do this sort of attack. And I'll go ahead and number the atoms like I was before. And then you can start by drawing the ketone we started with. On the alpha position, we formed a new bond here. That's alpha, this is beta. Again, there should be an alcohol at the beta position. And then we have an ethyl group and the methyl group attached there. Because this is like carbons 1, 2, 3, and 4. So that's the aldol product. And again, draw both aldol products unless he says otherwise. So you should also draw this condensation product. Okay, next one has another ketone. And you might think from precedent, like we've been doing aldol reactions, this one also involves a base, it must be aldol. But this is why it's important to pay attention to conditions, because you know, on the exam, you're going to get a mixed bag of reactions. It's going to be stuff from recently and maybe even stuff from 112A. It can be a lot of different stuff. So you got to pay attention to what's on the arrow, because ketones and aldehydes can do a lot of reactions. Here, we are adding a base, we're adding LDA, but this is a strong base, and we're adding one equivalent of it instead of a catalytic amount. like we were with aldol, and we have this cold temperature. So remember to connect these conditions, one equivalent LDA, cold temperature. This is direct alkylation. Not aldol. So that means we're going to form an enolate. Well, like it's going to start the same way an aldol would. It's just instead of reacting with another ketone, it will react with this alkyl group. And it's going to form on the left side here because this is the less substituted side. And then it will react with our alkyl halide, which looks like this. So it does this SN2 attack. It's a propyl group here. So that was that. Next one has another aldehyde. This time we have catalytic sodium hydroxide. So again, aldol conditions. So I'll start by drawing this enolate, and it will be attacking another copy of a neutral aldehyde. Looks like this. This will be the nucleophilic attack. And I'll say the aldehyde carbon is carbon 1, this is 2, and then phrase like where the benzene ring is, just to sort of keep track of things. I'm going to be starting by drawing the aldehyde that we started with. Again, at the alpha position, you're forming a new carbon-carbon bond. This is in green. And then there should be an alcohol at the beta position. Remember, this is always the case for aldol reactions. And then put the rest of the structure for the electrophilic aldehyde. And this is like 1, 2, and then 3. So that is attached the right way. And then again, also show the condensation product. So you have your aldehyde. At the alpha position, we form this alkene towards the beta position. And then you have the rest of the structure. Okay. And last one on question 5, we have an aldehyde and we're adding catalytic hydroxide again. So again, these are conditions for an aldol reaction. But this time there are 2 aldehydes in our starting material. We have the one on the left and the one on the right in the same molecule. It's like it will start the same way because we're adding a base. It's going to form an enolate at the alpha position. And theoretically, it could do a reaction like this with an aldehyde and another molecule, like so. That is a thing that can and could, like it will probably happen to some extent. But this is an intermolecular reaction between 2 molecules. And we have another neutral aldehyde right here in the same molecule. So the enolate will prefer to attack this because it's in the same molecule. It's closer, they don't have to bump into each other in space, so it will be a faster reaction. This will be something that I've said before, and like it's important to remember. Intramolecular reactions are always faster than intermolecular. Regardless of the context, intramolecular is always faster than intermolecular. So always be on the lookout for like when you have two things in the same molecule, they can react with each other given the right conditions. And that is going to be what happens here. This intramolecular reaction is going to happen. And then I would recommend numbering the atoms from nucleophile to electrophile. When you do that, numbering from the enolates to the carbonyl carbon, you see it's 5 carbons, so we're going to form a 5-membered ring. And then we have our aldehyde here outside of the ring. This is 1, 2, 3, 4, and 5. And we put the alcohol here on carbon 5. That's where the aldehyde that was the electrophile was. And you can also see that that is the beta position. The alcohol is beta to the aldehyde, so that makes sense. And then you can also show the condensation product with the conjugated alkene. And that will look like this. So, like in the past, be on the lookout for intramolecular reactions. If you have the right conditions, they're going to be the main thing happening. Okay. Here, I'm giving you products that are from Aldol reactions, and I'm asking you to figure out what the starting materials were that you used to make them. And being able to approach this, like, I don't know if you would be given a question exactly like this on an exam, but even if you're not, like, being able to figure out, like, what you used to make a product, like, that's kind of the thinking you need to do synthesis. If you can recognize like how you made a certain product and you can connect that with a series of reactions, that's what synthesis is. So if you can figure out like how I made this, then you could potentially figure out how to connect that to some other things to like do a whole synthesis problem. So this should be good practice. And to work backwards, you can think of it as like sort of break the bonds that you formed to make this product. This is the alpha position, alpha to the aldehyde. This is beta to the aldehyde, where the alcohol is. And remember, like in the past today, I was showing that new carbon-carbon bonds we formed at the alpha position as a green bond, just to emphasize like that was the new bond we were forming. That's this bond that I've highlighted in green here. So that's the bond we made. And if we're trying to work backwards to the starting materials, you can kind of think of it as like just breaking this bond, break that bond, and then see like what was on the left side and what was on the right side. And then those two things, when you added them together, that's what gave you this aldol product. So on the left side, I have this part I've circled in blue. I'll go ahead and draw that. And then on the right side, I'll circle this in orange. And remember, this alcohol, like if you consider the mechanism, this alcohol formed from a carbonyl, like the carbonyl got attacked, and then you had an alkoxide and you protonated, that's where the alcohol came from. So where this alcohol is in this structure, that's where a carbonyl was in the starting material. So if I replace the alcohol with a carbonyl, you see you have an aldehyde. That was what was in the starting material. And if we number these atoms, you see like they both have 4 carbons, 1 aldehyde. It's the same structure. So you could have theoretically, you could say something like this too. Just put 2 and then draw the structure like this to say there's 2 of them. But if this was on an exam, I don't think it would hurt at all to just draw it like I did here. Just draw both of them. And then once you draw them, you see they're the same, but it doesn't matter necessarily. You could just say they're the same thing as a note or something, but it's better to be safe. So probably going to go through it a little faster on the next ones, but this is the general process I would use to like work backwards from the product to the starting material. Identify what bond you made, like which new bond you formed to make that product, break that bond to kind of cut the structure in half, and then figure out what you started with to make it. Okay. Again, like gonna look at it the same way. So this is the alpha position, alpha to the ketone. This is beta. And this isn't the aldol product with the alcohol, but it's the condensation product with this conjugated alkene. And this conjugated alkene is between the alpha and beta carbons, and that is the new bond that we formed to make this product. So if we want to work backwards, we can break this bond between the alpha and the beta carbons. And then I'll draw the structure that we get from the starting material on the top that I've circled in blue. That's one of the starting materials. And then on the bottom is this structure. And we don't have an alcohol to kind of give us bearings on like where the carbonyl was, but like where that double bond was, like on the carbon that was beta in the product. That is the carbon where a carbonyl was in the starting material. So like draw the skeletal structure of that part I circled in the bottom. And then that carbon that was beta before, which is the carbon in the middle, that's where a carbonyl should be. So it's a ketone. And again, it's the same 2 ketones, but it doesn't hurt to draw both of them. And then you could just put a note like saying, oh, they're the same ketone, same structure. And I would recommend doing that if you had this exact question somehow, just so he knows, so Kuda knows, like you recognize it's the same thing. It's not 2 separate things. Instead of erasing it and putting a 2 here or something. But either probably be fine. Next one, similar approach. This is alpha to the aldehyde. This is beta, where the alcohol is. We formed the bond between the alpha and the beta carbon. So if we want to work backwards, we should break that bond. I'll go ahead and draw the structure I have circled in blue. That's starting material. So you get this ketone. And then I'll also draw this structure that I circled in orange. And if we number these, that's like 7 plus the phenyl group. This is also 7 plus the phenyl group. So again, it's the same structure, but it doesn't hurt to draw both just to make sure they're the same structure. So this might seem like a simplified kind of cheating way to do this, but I can promise you with like 99.9% certainty that like if you're trying to work backwards from an aldol product to a starting material, approaching it this way will work like all the time. I can't think of an example where it wouldn't work. And it's good to be able to figure out what you used to make a product. That's a big chunk of what this class is. So feel free to look at these kinds of problems in this way. I think it'll make it a bit easier on you. And last one on the worksheet, gonna approach it similar way. This is alpha to the ketone, this is beta, where the alcohol is. This is the bond we formed to make this product between the alpha and the beta carbon. If you're working backwards, break that bond. Now I'll draw this part on the right that I've circled in blue. That is one part of, or that was one of the starting materials. And then the left side of the product, I'm circling in orange. This will be the ever product. And again, remember where the alcohol was in the aldol product. That was a carbonyl in the starting materials. So that's how we can approach this drawing. You have a benzene ring, you have a carbon, and then there's a carbonyl here. And then there's no other carbons, so it is an aldehyde. And this time you can see like it's two separate things. We have a ketone and an aldehyde. They're not the same structures reacting to form this aldol product. And examples like this are why, like, even if you're pretty confident that it was two of the same thing reacting to form the aldol product, I would recommend like doing this whole process to make sure it's two of the same thing. Because there will be cases like this where it's two separate things. And you'll probably see this in class on Tuesday, where two separate compounds react in an aldol reaction. And I'll have more examples of that on the next worksheet. But that is all I have for this worksheet. So, like I said at the beginning, feel free to email me with any questions that you might have, or if you want to ask questions about this worksheet on Tuesday or whenever the next meeting is that you come to, feel free to. And I will be posting some synthesis problems to practice that we probably won't be going over during the workshop, but you can also email me about those. And good luck studying. I will see you guys next time.